KTH, and we will speak about non-univalent solutions to Polubarinova-Galin equation.
Okay, thank you very much, and thank you, the organizers, for inviting me here. It's a great honor to be at the Newton Institute after having, in my case, working with the Newtonian potential theory for related matters for, more or less 40 years. So, so the title of my talk is something with a Polubarinova-Galin equation, and this is all about a flow problem called Healy-Shaw flow. So, Healy-Shaw was a British engineer. I think he was born 1854, and he lived quite long. And he became famous for a moving boundary problem, which nowadays is very it's in the center of interest in many areas of research. And nowadays this is also called this problem is also called Laplacian growth. So it's a fluid problem in 2 dimensions, and actually it's about a viscous fluid like oil, which is squeezed between 2 plates. But for simplicity, let's just think of having so we have a blob of water, for example. So let's say that we have a water leak in our house, and there comes up water, and this is a blob of water or some fluid. So here is the source point. And so as there comes up more water, this blob will grow, of course. And in this talk I will be interested in what happens in a situation like this, when two part of the water fronts meet each other. Okay, so let's first draw some pictures. So the next stage will naturally be something like this. So now, well, this should be bigger in all respects, but after some time it will look like that. And for the physical problem, the natural continuation will be that these parts join under the flow. So from the beginning, this flow region, it depends on time, so I will call it omega of t, and everything is part of the 2-dimensional plane, and I will use complex variables in this talk, so this will be the complex plane. So after some time, as time goes on, the blob becomes multiply connected, and it turns out that this can be very well handled. This is actually mathematically the problem can be treated by using weak solutions for the iron. So I have not yet written up any equations, but I will do it soon. I don't know if Charles Elliot is here, but he's so like 35 years ago, Elliot and myself and a few other people independently developed the notion of weak solutions for this problem, and they work very well, and they are even global in time, so you can continue this water leak forever. But now, today I will be interested in another way of continuing this solution. So another, and this is so I want to insist on keeping the fluid domain simply connected all the time. And simply connected means that there are no holes like that. So to get it, if you want to keep it simply connected, this will result in a kind of overlap like this. So the source point, I will take it to be the origin in the complex plane. So one can imagine kind of this flow kind of going on some different planes, so that they overlap a little. And so this is still okay in the beginning here, but rather soon one will get into troubles. So if one continues this way after some further time, there will appear a singularity, a kind of a cusp, and so up to here it's okay, but then the problem starts at this point, and that's the problem I want to speak about. Okay, so in order to say something more specific, so let's write up the equation here for the flow. So the dynamics for the Healy-Shaw flow, it's that the boundary of the domain, it moves with a velocity which equals the gradient or minus the gradient of the Green's function of the domain. Let's say that this is a point z, and so the Green's function of z, and it also has a pole at the origin. But this Green's function, it depends on the domain, so it changes with the domain, and it has boundary values 0, and it has a pole at the origin, so I usually normalize this pole in this way. Okay, so actually even inside the fluid domain, the fluid velocity will be this gradient all the time. So in particular, the boundary has to move in that way. And so when insisting on keeping the domains simply connected, then a natural tool will be to use a Riemann conformal map from the unit disk to this fluid region. And so in general, this is the unit disk, and so this is the z plane, and this is the theta plane, say. And we take the map which takes the origin to the origin and call this function f of theta. So now I don't know how much the students know about conformal maps here, but actually it's rather easy to explain how this works in the present case. Because if you want to think of this from a physical point of view, you can think of the origin here, the source point, that you have an electric charge here, and that the complement of the domain is a perfect conductor. And this will mean that negative charges will gather on the boundary, and you will get an electric field inside here. And this G will be the electric potential for that field, and then the outer boundary here will be a potential, a level line for this potential. And if you look for other level lines of this potential. So this is a line where g that equals some constant. So this will be equipotential lines, and perpendicular to these lines you will have kind of the lines according to which the electric field goes. So the electric field is a vector field and is directed perpendicular to these level lines. And now if you do the same thing for the unit disk here, so then the corresponding potential equipotential lines will be circles, and these field lines will simply be radii. And what this conformal map does is simply that it takes corresponding points to corresponding points. So like here, so it kind of moves, goes between these two pictures. So now we can take this dynamical equation. So this is in some sense the Healy-Shaw equation, and it's also equivalent to Darcy's law in the theory of porous media. So it's and also related to many other things. But if we write up this in terms of this mapping function, we get what is called the Polubarinova-Galin equation. And it says that the real part, so f is a function of a complex variable theta and of t. So the time derivative I will denote by a dot. And so the exact, maybe I shall write out the variable series. So and the derivative will be taken to the complex variable by prime. So this is a Polubarinova-Galin equation. So this is equation which is to hold just on the boundary of the unit disk. So this is, and there are two names here. They are both Russian mathematicians, and Polubarinova, this was a woman, a fantastic woman really, because so if I write 1924, this is not the year when she was born, but this was the year when she wrote her published her first paper. And her last paper was published in 1999. So she had an active period of 75 years, and she was born actually 1899. So she became almost 100 years ago. And I don't know, maybe Eliot or John King there was a conference in Moscow this year in order to celebrate her 100 years birthday. But unfortunately she passed away 4 days before or something like that. But so this is a remarkable woman. Okay, so let's see, okay. So this is one equation, and now I want to reformulate it into another equation, which is called it's a Löwner-Kufarev type equation. So just to make take this equation and just divide both sides by f prime times f prime bar. So bar here is complex conjugation. So then in the right member one gets modulus f bar squared, and this is to hold on the boundary of the unit disk. So this is actually the same thing, but the good thing here is that one can now cancel two factors, and what remains is this equation on the boundary. And now I forgot to say something here, namely that this mapping function shall be normalized. So it should take the origin to the origin, and so if you write up the Taylor series, this starts that way, and so the additional normalization is that one chooses the first coefficient to be positive. But as you see from this normalization, the function you have here, it's holomorphic in the unit disk. It's an analytic function. So here one has an analytic function, the real part of which equals something on the boundary, and this means that one can solve this equation, and if one simplifies a little, so the result will be this thing here. It will be the Poisson integral, or Poisson-Schwarz integral over what is in the right member here. So let's call it just P for Poisson-Schwarz. So this P, it's something like 2 pi I, and integral, I think. So I hope I get it right now. So I forgot. Should have this factor also, which is important. So all this is an equivalent formulation to the Polubarinova equation, and this type of equation is usually called a Lerner-Kufarev equation. So Kufarev was another Russian mathematician, and Lerner was born in what is now the Czech Republic, I think. Okay. So this equation will play some role now when we are going to analyze what happens here. So I have to look how far. One may start, or let's take an example here. Let's take f simply to be a polynomial of degree just 3. And then the derivative of f, it will be a polynomial of degree 2, so it will be some constant, and it will have 2 zeros. Let's call them omega 1 and omega 2, and they will depend on time, and the coefficient in front will also depend on time. So where shall I? So let's go back to here now. So I don't want to. So what I want to do is to discuss how this development is related to the motion of these two zeros. So here we have the conformal map to this domain, and then these two zeros will be outside the unit disk. So f is what is called a univalent function. It's 1 to 1. So this means that the two zeros here are both outside the unit disk. And in the future I will call this function also g, by the way. So f and g are basically determined by these two zeros. So in the beginning they are outside the unit disk. And so what happens now at this stage when they start, the domains start to overlap, and eventually we get the singularity. It is that one of the zeros, let's say omega 1, it moves into the unit circle, and the other zeros stay outside there. So this is on the border of being locally univalent. But here we see in the equations now that this will cause problems. So if f prime has a 0 on the boundary, then it will be very difficult for the left member to be equal to 1. So this would force, for example, f prime to be infinity or something like that. Whatever, it will be a problem in any case in this equation. And similarly here, if f prime has a 0 on the unit circle, this integral will not be defined. So this would be no good if omega 1 is. So the problem we are trying to solve is to try to go on from this point of view. So is there any continuation whatsoever, or does the solution just stop here? And let me say it in the, as follows. So assume where we have been able to get into the unit disk with one of the zeros. So one is outside and one is inside. This will be no problem for neither the Polubarinova-Galin equation or the linear Kuhn equation. Whenever a zero is inside, at least the equations make sense and one can apply them. But but is it really possible to pass here? And so this is a main result I'm discussing today. So it's a joint work with Lin and myself, and it's actually not yet finished. But we hope to finish it this year. The result is true in any case.
Can I ask you a question?
Yeah.
I don't understand the points the omegas. Do you choose them yourself, or do you give them?
No. Okay. Yeah. Yes, I was maybe a little fast here. So if you take any one of these equations, so let's say it in this way. This is an ansatz. So you just suppose that your initial domain is given in this form, and then you try a solution on this form and just plug it in. Then you will get equations for the coefficients, and it turns out that you can solve them. You can figure them out. So even in general, so denoting the derivative again. So this is also a theorem, but it's rather old. It's actually a theorem which goes back to this old people. This equation was formulated in 1945 for the first time, and already at that time these people, or people in their research group, realized that if you start with a mapping function such that the derivative is a rational function, so then there will exist a unique solution with the again rational. So actually rational. The form, so generally speaking, so it may have both zeros and poles. So the general form of such rational function will be something like this. So omega k for the zeros and theta j for the poles. So if you start with something like this, it turns out that you can keep it that way, and everything comes down to a dynamical system for the motion of the zeros and the poles. So actually quite interesting dynamical system. So if you let's say that you also have two poles here, so the zeros and the poles will move all the time, and this this dynamical system will be equivalent to the Polubarinova-Galin equation. But the poles turn out to behave much better than the zeros, so the poles always move away from the unit circle, while the zeros sometimes reach the unit circle, and in that case they cause problem. Okay. So the main result now is that given any initial mapping function, it may be rational or not, there exists a global in time, so for all t up to infinity, solution. It must be a kind of a weak solution to the Löwner-Kofayev equation. And for this weak solution, the zeros of the derivative may have zeros inside the unit disk. I may continue on this board. The solution cannot be a strong or classical solution because of these problems we saw when you have a zero of the derivative on the boundaries. So one has to use a weaker concept of solution. So if this theorem is true, so what would happen then after this stage? It's a little, the only way it can be is that the fluid region swallows this cusp, whatever you want to call it. So this point here, that point is F, the image point of this zero, which is on the boundary. So in the continued process, this will be inside. And what about the zeros then? Well, so omega has gone inside and omega 2 will be outside. But it turns out that this is not all. So in order for omega 1 to pass a unit circle, a certain price has to be paid. And this price is that it creates 4 new particles, so to speak, actually 2 more zeros and 2 poles. So 2 zeros plus 2 poles are created. So not only will this zero be inside, but there will be 2 other zeros, omega 3 and omega 4, and moreover there will be 2 poles, omega 1 and omega 2. So this is the only way you can enter with a zero, and we shall see this in some detail in a while. Okay.
May I ask you, bother you with another question?
Yeah, it's fine.
You started with telling us about keeping simply connectedness.
Yes.
But so you're working on a Riemann sphere, I guess.
Yeah. So
what
now, the path I also have to pay is that we have to work on a Riemann surface now.
Yeah. So how do you define simply connectedness here?
Yeah. So I simply count the unit disk as simply connected, and F is the image. So one has, let's say it in this way. So this weak solution is actually identical with the old weak solution I mentioned in the beginning. It's kind of a variational inequality weak solution on a Riemann surface. Let's call it R. But the problem with this Riemann surface is that it's not known in advance. So you may think of this as being, now this F is not univalent, it's not 1-to-1, because points in here are, values in here are taken twice. But there is a way to view it as a univalent map, and this is, let's then change the name of it and call it f tilde. So this is omega of t, but and now I consider omega tilde of t as part of a Riemann, kind of a Riemann surface. I don't know how to write it here, but if we define a Riemann surface properly, this we can make this f tilde 1 to 1, and the domain omega itself, it's a part of the complex plane, and this Riemann surface R, it's a covering Riemann surface of the complex plane. So let's kind of remove now. So the usual way one writes, so usually one writes the Riemann, we have a Riemann surface above the complex plane, and here we have a covering map which may be branched. So f goes this way and f tilde goes up here, and it should be viewed as this one will be univalent. So I have 20 minutes, so I hope in these 20 minutes to kind of explain the details of this, because it can in fact be explained even if it looks mysterious. So one of the key observation is so f is not 1-to-1, but f tilde is 1-to-1 when we look at it in this way. So a little lemma here is when the map f is not 1-to-1, then the Löwner-Kufarev and the Polubarinova-Galin equations are no longer equivalent. So when f is not necessarily univalent, write it as 1-to-1, then so the Löwner-Kufarev equation is a stronger equation. It's quite easy to see, but I will not go into the details here. It's equivalent to the Polubarinova equation together with the fact that those zeros, let's say it this way, whenever you have a zero of f prime which is inside the unit disk, the image of this zero does not move. So this is for all k for which omega k is inside the unit disk. So in the picture here, let's say, what the second last thing is saying here is that the point here, the point here, so this is f of omega 1, say t. This point does not move when time increases. So this you need to have in addition to the Polubarinova-Galin equation in order to get the Kufarev equation. So this is easy to see, but I skip the proof, but well, so you may easily see. If you evaluate this derivative, so there's 1t in here, then you have no, sorry, f prime, and then you take the time derivative of omega 1, and then you have something, an f dot here. So if you evaluate this total derivative, so by definition the first term disappears, and you just get a condition that f dot, the derivative with respect to this t, vanishes at the 0 of omega k, which is in fact has to do because of the Lerner-Kufayev equation, as you see immediately. Okay, so we'll finish with an example which is supposed to illustrate how the theorem works, or how it works under this transition here. Maybe we start, let's take a number, a positive number a first, and let's start with no fluid at all. Okay, so then of course so if you start with nothing, then the fluid evolution will just be a family of increasing disks. So here we have the origin, and so A is a positive, lies on the positive axis. So here we have our water leak, and eventually this reaches the point A. And okay, so suppose now that we live in a villa with two floors, and we have a water leak on the upper floor, and this is a staircase to the lower floor. So then we'll go down water to the lower floor. So this is the upper floor. And these two floors, this will be the Riemann surface. So this is the upper floor, and this is the lower floor. So we start the fluid here, and so let's say here is this point. So then there goes down some water go to the lower floor, but it also continues on the upper floor. And the Riemann surface in the theorem, it will be a two-sheeted Riemann surface. With this point A, it will be a branch point. Because you can go from one floor to another via that point. And what you end up with is actually the Riemann surface of the square root function. R will be the Riemann surface, the classical Riemann surface. This over the function z minus a. If you take this function, square root of z minus a, and want to make it single valued, you have to create a Riemann surface on which it becomes single valued. So this is what R will be, and let's call this square root Z tilde. Okay, so let's write all this again, but in a different way. So here we have R, and here we have the complex plane, and we have origin and the point A, say. And the usual way one writes this is actually something like this. The two sheets kind of interchange at the point above A. And so here is a variable Z, and the variable Z tilde would be the variable up here, or yeah, this would be a kind of a univalent or a single valued coordinate on this Riemann surface. And from the upper to the lower we have a kind of projection map, this branch covering map. So the branch covering map in this coordinates, it will then be simply, if you simply invert that relation, you see that Z will be Z tilde plus A. So that will be the form of the projection map. And the water leak is now at a point above the origin, so let's call it 0 tilde. And in order, everything then reduces to a Healy-Shaw flow on R. And when one expresses the equations for Healy-Shaw flow on this Riemann surface, it will be the same as the kind of weighted Healy-Shaw flow. So it becomes weighted Healy-Shaw flow when you express everything in the coordinate you have up there. So I can write up in more detail. What it looks like, but maybe I should skip. One way to write the dynamics, a convenient way, is to say that whenever you have a harmonic function, you integrate a harmonic function over the domain, it will be equal to this harmonic function at the origin. So this is the dynamics in C, and to get the dynamics on R. So what you have to do is that you have to lift. Harmonic functions make sense also on the Riemann surface, but this area form you have here, dx dy, this has to be lifted up, pulled back to R by this projection map, and then it becomes in general the derivative of this projection map squared, modulo squared. So this is what the dynamics will look like on the Riemann surface. And now, so the point, the origin here, which is z equal to 0 here, it will actually be the point I to square root of a here. So if we really write down what this means, so in our particular case, so this p prime will be 4 times z prime z tilde squared, and this 0 is the point which has a z coordinate equal to minus I, and in this coordinate the Hileshoff flow will look different. So it's something, it will look something like this. So now in R, in the coordinate z tilde, the source point corresponds to I square root of a, and the fluid regions, because you have now a weight in the Hileshoff flow, the Hileshoff flow, the weighted Hileshoff flow will not no longer consist of just circles, but it will look something like this. And when we come to the branch point here, there will be a singularity of the boundary which is 90 degrees, because the square root function it's exactly what needs to make this angle open up to 180 degrees, and then it continues in this way. So this is a weighted Hileshoff flow on R in the coordinate z tilde, which correspond to the original one. And eventually, so I may write up the explicit solution. I can do it here. So. And from this, if you believe in this explicit solution, it will show that these additional zeros and poles come up. So I have to check here. And you will also see that it will also be a weak solution. So f, the function we had from the beginning. So at first it's just conformal maps onto growing circles. So it would be some constant time t times the variable. So let t equal 1 to be the critical time when we reach this staircase. But after that it will change character. So it turns out that it will look this way. So this is what it will be after time 1. Essentially, so except for some scaling of times and so on, which I did skip. And if you let's look at the derivative of this. So if you take the derivative of constant time theta, it will be simply this theta. And if you take the derivative of the time t, it turns out that you will get an expression like this. So this is for t greater than 1. So at first you have a very trivial derivative, just a growing constant. But then, when we come to this critical point, there starts this cascade of new zeros and poles being created. That's the price we have to pay to get into the unit disk. So I had to add this factor, which is actually on the formula which I wrote before. There are 2 zeros and 2 poles, and moreover there is a certain structure here. So saying actually the 2 poles are identical, really, and in addition, so theta 1 equal to theta 2, they are both equal to t, and this is 1 over, it's a theta 1 over the 0, or actually 1 over the conjugate of that 0 which is inside the unit disk. So there's a special relationship here. But this is what it looks like, and so now I'm finished. So just one more word, maybe since Alain Sola is here. So the factor which comes up here, this factor, let's call it f, simply so. This factor is a contractive zero divisor. So in the sense of so one of my colleagues, Håkan Hedenmalm, some 20 years ago, he made important progress in the theory of Bergman spaces by being able to construct certain kind of contractive zero divisors, which has a property that so when you integrate an arbitrary analytic function against such a zero divisor, you get the value of the function at the origin, and this function has certain prescribed zeros, and this is actually what you get here is actually a special case of this, and it's a general fact. So that's a Hiller-Shaw evolution on the when you insist on keeping it simply connected all the time. The zeros you get inside, or the extra zeros and poles, this will make up such a zero divisor. So, okay. So maybe this was not a very understandable to most of you, but anyway, so this was more or less what I wanted to speak about. So thank you very much.
Thank you. There are questions or remarks?
Yeah.
Maybe a question about this zero divisor thing. So in the framework of polynomials or rational functions, you're only going to get finitely many zeros moving inside the disk, right? Did you think this is something that's going to be true even if you, if you're able to do this for more general functions? Can you get more than finitely many zeros.
Well, more than finitely many, I don't know. But I guess I can get all zero devices which are just finitely many. So the remarkable thing with this is, so by the mean value property of harmonic functions, this identity holds for all analytic functions H. But the remarkable thing is that you can get the same thing, but with maybe there should be a conjugation here. Also with so you can allow a factor which here with prescribed zeros and which also has certain additional properties. So by coincidence, this, well, it's not a coincidence, but it's a remarkable coincidence that come up here from a completely different point of view than what Hedenbaum had originally. And this function also appeared in some work of Makoto Sakai, a Japanese mathematician. Related work he worked on what he called quadrature domains on Riemann surfaces. I didn't answer your question, but I don't, because I simply don't know the answer. Okay.
Other question? Remark? Not? Thank you.
Okay.